Let's discuss the ideal transformer. Many of you have used transformer or at least have seen transformers. It's one of the very basic element of power systems. Um, this is, as you can see in these pictures, this is the construction of transformer. Very simple. You have two loops of wire or inductors, you can call them, and they are wrapped around on an iron core in this one as well as in this one. And this is the electrical symbol of transformer. The core can be iron core or it can be air core. So your transformer can be either an iron core transformer or air core transformer. The basic idea is that when there are two sides of transformer. This is the primary side. The voltage of the primary side is represented by Vp, and the secondary side Vs. So the source, sinusoidal source, is connected to the primary side and the load is connected to the secondary side. So we're going to discuss the basic fundamental working of the transformer in the next topic. But in general, as you can see in this picture, what's happening here is when you connect a power supply on the primary side, then sinusoidal current starts flowing in the loop of wire. And as we know from the Faraday's law of electromagnetic induction, sinusoidal current, since it is time dependent, it will produce a sinusoidal flux in the coil, and then sinusoidal flux is going to go through the iron core as well as through the air. But since the iron core is more can carry more flux, has less resistance, so it's going to, in this one, it's going to go through the iron core and is going to be linked with the secondary coil. And once again, when the time dependent flux is going to be linked with the secondary coil, a voltage will be induced on the secondary side per Faraday's law of electromagnetic induction. So that's a basic working of the transformer. So you can go through the notes. As I said, you have the iron core transformer, then you have the air core transformer where there is no iron core, and the flux is linked through the dielectric or the air present between the two coils. How ideal transformer differ from the practical transformer? So ideal transformer differ from the practical transformer in these three respects. We assume that all the flux that is produced by the primary is going to be linked with the secondary, and that's called mutual flux. There's also leakage flux, which is produced by the primary and it does not link with the secondary, but we assume that the leakage flux is zero. We also assume that there are no hysteresis and eddy current losses, as we discussed, that there will always be hysteresis losses and there will be eddy current losses. Actually, if I go back up and I show you, look at the lamination. So these laminated iron core is going to reduce the eddy current losses, but for the ideal transformer we assume that they are zero, and we also assume that the coils have no resistance. Primary and secondary coils have no resistance. So these are the fundamental differences between the practical and ideal transformer, that we assume that this is valid for ideal transformer and these are invalid for practical transformer. Well, in this course we are just discussing right now for ideal transformer. Practical transformer are not that different as far as analysis is concerned, but we don't really have time to go over practical transformer, which is supposed to be the next chapter, but we are not going to discuss that. What are the applications of transformer? Most of you know why we use transformers. From the first application, that is, it is step up or step down the voltage and current. So that's the most important application of transformer. Either it's going to step up the voltage or step down the voltage based on the number of turns on the primary side and the secondary side, as we will discuss in the next topic. Also, transformers are used to step down and up the values of resistors, inductors and capacitors which are connected on the secondary side. So on the primary side, the source see a different value. And likewise, if you look on the secondary side towards the primary side, then on the load side you also see different values of the components that are connected on the primary side. So basically it is used, for example, if you do not have a capacitor value that you want to use, but you have a transformer, then you can use some other value of capacitor. You have to calculate that value. Actually, one of the problems will be to calculate that value. You can use another value of capacitor connected on the secondary side, such that due to the presence of transformer on the primary side, the source is going to look at that capacitor value, not the actual value that you're connected, but a different value. And again, we're gonna discuss that in the following topics, one of the following topics. And transformer is also used for circuit isolation. It isolates the primary side to the secondary side such that any load that you're connected on the secondary side, it does not load the primary side down. So it's a very common application, especially for the electronic circuits. So to understand how the transformer works, first we're gonna look at the concept of the voltage induced in a coil, which we have already discussed, but more importantly, the concept of the sinusoidal flux. So we know that Faraday's law of electromagnetic induction, when a sinusoidal current is going to flow through a coil, sinusoidal flux is going to be produced. And let's assume that the sinusoidal flux is given by this equation. Phi t is equal to phi p, where phi p is the maximum or peak flux, cosine omega t. And according to the Faraday's law of electromagnetic induction, induced voltage is n d phi over dt. So we go ahead and put this equation and take the derivative with respect to t, and we are gonna get n omega phi p sine omega t. And if we want to take, since it's a sinusoidal quantity, induced voltage is sinusoid with the peak value of n omega phi p, then the RMS value of that induced voltage, of course, is the peak value divided by square root of 2, as you can see over here. And that will come out to be, omega is 2 pi f, that will come out to be 2 pi over square root of 2 is approximately equal to 4.44. So 4.44 f n phi p, that's the induced RMS value of the voltage. Alright, so what is the basic concept of when you apply the sinusoidal voltage to a coil? So when you apply a sinusoidal voltage to a coil, current is going to flow, of course, sinusoidal current, and that current is going to create a flux which will also be changing with respect to time. It will be sinusoidal flux. Now when this sinusoidal flux since the sinusoidal flux is linked with the coil, of course it is produced through the coil, so it is linked with the coil and it is changing with respect to time, then according to Faraday's law, of course, a voltage will be induced in this coil. And that's a fundamental difference, as if you do not have the coil and have just a straight wire, and if you convert that straight wire, if you wrap that straight wire on a pen and make a coil and make an inductor, that's a fundamental difference, because a straight wire is not really going to produce any flux, hence no voltage will be induced in there. But if you make that straight wire in a coil shape, then of course a voltage will be induced, because the coil is going to produce a flux which will be changing with respect to time, and that flux is going to induce a voltage in the coil. So that means you have ES, applied voltage, and E1, induced voltage. In this case, of course, ES and E1 will be same, because we are assuming there is no line resistance over here. But if there is a line resistance on line reactance right here, then of course ES and E1 will be different from each other. But that's the concept of applied and induced voltage. Now since the current here lags the voltage in inductor by 90 degrees, hence the current in the circuit will lag the voltage both ES and E1 by 90 degrees, since ES and E1 will be same in this circuit. So if you look at the phasor diagram between the voltage and current, this is going to be the phasor diagram. ES and E1 at 0 axis, and current and flux are 90 degrees out of phase, where they're lagging the current, they're lagging the voltage by 90 degrees. Okay, before we go to the next topic, let's look at an example.